topics that I mostly teach about as well at James Madison University. So I'm in the Geology and Environmental Science department, but I do teach Gen Ed classes. This semester I'm teaching a big Gen Ed of 110 students, and it's on Earth systems and climate change. So it's looking at climate change from a geological perspective. And then I teach an upper level class for majors, and that is actually the title of the class, Paleoclimatology and Paleoceanography. And that one is more targeted for people who are wanting to go into this field, or they're getting some interesting electives in their geoscience major. So, I'll use the right computer. Let's see here. Okay. So, my understanding of how the program works is to try to give you a sense of how a certain type of field does their science. And so, in what I'm going to, my goal is to provide a glimpse of how paleoclimatology and I have / paleoceanography is done, like the ways that we go about addressing this. And I'll talk a little bit about what I do specifically, but also I've kind of broadened it out to this field overall, because it might be a field you don't know that much about, and your students might not know that much about. But studying past climate is super important, because that's what gives us the context, the foundation for understanding what's going on with climate now, and it gives the grounding for climate models for future climate predictions. So we have to understand what's happening in the past. In fact, climate models, to test them, they are first tested against the paleo records to see if they can match that data. And so that's what I do for research, and it's been, I didn't even know what that was when I was going to college or when I was in high school, and now I'm doing it. So that's something that maybe you had the same experiences, I'm not sure, but your students I bet will too. There are going to be fields that if they don't know about now, might not be taught very much in school in the pre-college levels, but it could open up all sorts of doors for them if they're open to the opportunities. And I wanted to show, there's a great article in National Geographic, and it's several years ago, but it talks about a particular time period in Earth's climate history where climate changed very rapidly from a time that was already warm to super warm. And this is a time period about 56 million years ago, and it's something that will come up a little bit in a video that I'm going to show you. God willing that it'll work later on, but to just give you some contrast, this is a picture from National Geographic about kind of framing this interesting time in Earth's history. So here's a picture, of an Inuit standing in Baffin Island area near Greenland, northern Canada, and this is South Carolina. But this is what that piece of property would have looked like at that time, and it's not because that piece of property was way down where South Carolina is. So these extremes of climate are something that I find really fascinating, and I'm glad I get to work on it. So the way I want to go about the presentation is I'll talk just a little, very little actually, about my career path, but I can do more in question and answer time. And then I want to give you more of a sense of the nature of the research for studying past climate and past ocean conditions. And I'm going to do that with a video that I think I show it to my classes. In fact, they just had to watch it last week. And I'm also going to talk about, back to something that I am doing, is the planning that is going on right now for a coring expedition in the Arctic Ocean next summer. And then I've got, behind the doors over there, I've got some things some show and tell where you all can look at a real ocean core, a section of one that I brought that was recovered from the Gulf of Mexico. Some microfossils from that same core, a little bit shallower than the section I brought you. And then this is, to me, is like really cool. This is what I mainly study, is sediment transported by sea ice or icebergs. I reconstruct when there was ice in the past and where the ice was coming from by looking at sediment in the seafloor. So it's very puzzle-like. I'm reconstructing past climate by looking at an archive of where the material is now deposited and using the core to figure out what happened in the past. Okay, so I had a lot of college, and I'm still in college in a way. That's where I am. Like I love academia. I really do. But I went to Furman with the plan to be a political science major, and then I took my Gen Ed science class in once you're like at the next, past the intro classes. And even then, I really didn't know about studying climate change. I was kind of thinking maybe energy, maybe working for an oil industry, something like that. But I very much like problem solving. We talked about that. But I think even more is like puzzles. Really, not puzzles, but mental puzzles, trying to figure things out. So then I went to Ohio State and I did both of my degrees, my graduate degrees there, and got sort of more and more specialized, where technically I think my degree says geology, but really I am a marine sedimentologist. I study sediment from the ocean floor and subsea floor, and then I am looking at that to put together an understanding of past climate, or past ocean conditions, paleoceanography. And from that, those ocean sediments can also tell us about past climate. So while I was in graduate school, something else that opened up for me, because of the person I was working with, my research advisor, was getting involved in this international ocean research program. And it's changed the name over time, and maybe some of you have heard of some of these, maybe some of the people who might be more senior in the room might have heard of the Glomar Challenger, for example. And this is this legacy program. It's an international program, and a lot of what we know, most of what we know about past climate change for, let's say, like the last 66 million years is because of the work from this program. And it goes, you can see it's got derricks. They go to places in the world's ocean. There's a hole in the middle of the ship. They drill down, they lower pipe all the way to the seafloor, they drill like a donut shape, and they collect the donut hole as a long cylinder, and that's a core of ocean sediment or rock. And I've been involved in this program on several cruises, so I've been involved in these stages of it. And this is a map of different locations that we now call IODP, International Ocean Discovery Program. Different places they have cored the seafloor. The expeditions that I've been part of have been in these locations, and the star that is farthest right up here, this is one that I'll talk about. That's actually happening next year. So to get a picture of what a core looks like, in addition to the seeing one, there's some pictures here. This is a much younger me. And this was when I was part of the coring program in the Arctic Ocean. They were coring right here in the Central Arctic, on this ridge, the submarine ridge. And they were coring not ice, but getting to the sediment on the seafloor. And the goal was to reconstruct climate of the Arctic, because we had, at that point, we had no idea. We had no records for the Central Arctic recovered because of the technology that it would take to be able to go to this location and do what needed to be done. I was not on the ship at that time with them because I had a baby a few months before, so, wait, there's one of my yes, there you are, one of my son's teachers and my daughter's teachers. So when I was pregnant with Will, that was a little before this, and I wasn't able, I was not going to go to sea right away, but instead I joined them in Bremen, Germany, where we did much of the work that we normally do on some of these other research expeditions when we've got a bigger ship and less dangerous kind of place to actually do the science offshore. So, what I study is sand. Okay, so I study sand. It seems pretty simple. You see sand on the beach. Well, I study sand that's come from the seafloor. And if we pick our locations right, the sand can tell us a lot. Just the presence of us can tell us a lot. And so these are some various pictures of sand grains. I've got some in the room over there. And these are where I'm looking at some surface textures of the sand grains. And all of this is telling me about ice and it coming and going, its presence. And in fact, even some of the textures, I'm able to decipher whether it was transported by an iceberg or sea ice. So it's actually pretty simple tools. I use microscopes, some fancy microscopes and not fancy microscopes, and not much else. So it's not super high tech, but we've gotten some really powerful results out of this, including extending over millions of years, way farther back in time when the Arctic first became glaciated. So really like a shifting our understanding of some fundamental changes in climate. then I've talked about the sand. So, and I've used this word before, ice rafted debris. So the sand that I'm looking at, I work backwards. It gets to locations on the seafloor because of icebergs or sea ice. And the sea ice, because sea ice sometimes will form shore fast, it'll be right along the coastline, and it can pick up what's on the beach and in the shallow water areas on the bottom of the ocean there. It picks up that sediment, carries it out, eventually the ice melts, drops it, and there it is for us to try to make sense of later on when we recover it. Okay, so that's just a little about what I do, but I think what is much more useful is to show you guys a video, and I'm wondering if any of you have already seen this, because it's called How Science Works. And I'm not insulting your intelligence. There are different versions of this, but I'm showing you the one that specifically uses an example of people doing what I do at sea. I know some of these people. And they're studying climate change in a different location. It's one of the dots on that map. And it's about 10 minutes long. So we're going to do this. It also, I'll point out here, Berkeley has a whole lot of support materials that cover the same concept. And I have a handout for you, as if you were students. If you wanted to take notes, I'm just going to, maybe you take some, and then I'll put some over this way. Thank you. Just start passing them that way. Let me get the video going. And I'm showing you the video because I think this is a fantastic resource to understand how scientists approach studying past climate by looking at marine sediments. But regardless of what the topic is, it's a fantastic video. Just think about the nature of science and scientific investigation. So I'm going to go out of here, go over to here. And on the back of that worksheet, I'll tell you what's on the back of that worksheet later. So there are some questions there. If you want to take notes, you can. Let's see if it's going to work. Once I get the volume going. Hold on. I had it on mute.
Question? You make a hypothesis about what you expect to find. Perform an experiment to see if the hypothesis is correct. Science, the art of learning about the natural world around us. It seems straightforward. You ask a question. You make a hypothesis about what you expect.
No, it was to the left before you made it little.
All right. Sorry for the technology.
But
now it's down here. Let me do this.
Okay.
Right? Something like that. Is that good?
That'll work.
Science, the art of learning about the natural world around us. It seems straightforward. You ask a question, you make a hypothesis about what you expect to find, then you perform an experiment to see if the hypothesis is correct, you analyze the data and determine if you're right. Simple, right? Well, not really. There is much more to it than that, which is what makes science so exciting and fun. In fact, scientists often describe it as a process that is all about exploring, asking questions, testing hypotheses, and changing direction if their original ideas were wrong. All the while working and sharing with other scientists, advancing what we know about the world around us.
My experience is that I'm almost always wrong. That the original idea I came up with is actually not a very good explanation for the way nature really works.
Awesome! It's coral from an ancient atoll. Do you see?
All the time you're collecting information, you're asking new questions. That's the key part of science. It's not just one question and the answer. It is one question leading to a bunch of other questions, leading to a bunch of other answers, which in turn eventually leads you to a much more full understanding of the process.
So the real scientific process is not a simple linear one. This diagram shows the process can move in many different directions. There is often a constant adjustment of knowledge and of what the really interesting questions are. To show you an example of how science works, we are going out to sea with Dick Norris and his colleagues. Meet this group of Earth scientists who are fascinated by what can be learned about the climate history of our planet by studying layers of mud from the ocean's floor. They will drill down into the sediments and bring up segments of the sea floor in sections called cores. But first of all, why do they drill ocean sediments to study climate history?
Climate history is recorded in little tiny critters that die and deposit their shells in the sediment. Unfortunately, on land, sediment is usually eroded, and it's only in the sea that we actually find very well-preserved and continuous records of Earth history.
The scientists join an expedition on the scientific drilling vessel George's Resolution, affectionately called the JR. They will spend 2 months in the waters southeast of Newfoundland, Canada. So, what are they looking for? What's their quest?
We know that we are releasing carbon dioxide into the atmosphere. We know that carbon dioxide is a powerful greenhouse gas. We can measure the amount of carbon dioxide in the atmosphere today, and we can measure the amount of carbon dioxide in the atmosphere in the past. So the trillion-dollar question is, what is climate sensitivity? And that is the question that we are seeking to address with our expedition.
In other words, they are investigating how Earth's climate has responded to changes in atmospheric carbon dioxide in the past. Such research can help us understand changes we see today and better understand what may happen in the future.
We go back in history here and look at a time where we know the climate was extremely warm. And we found a place where we have an archive in the ocean sediments that we can read, and we can learn about the relationships between the oceans and the atmospheres, temperatures and chemistry.
About 55 million years ago, during what is called the Paleocene-Eocene thermal maximum, or PETM for short, the Earth was a very warm place. Thermal maximum means just that. Temperatures were very high. No land ice, no sea ice. Then about 34 million years ago, the planet suddenly cooled into a glacial world, much more like the one we see today. We figured this out by looking at the evidence hidden in the ocean floor sediments.
The core I'm holding in my hand contains sediment that we recovered from the deep South Atlantic. And these sediments span the Paleocene-Eocene thermal maximum. And so the lower part of this core has carbonate-rich mud. This carbonate-rich mud contains calcite shells of microscopic plankton. And then you can see a transition from this carbonate-rich sediment into a clay layer. And this clay layer is totally devoid of calcite shells. And this is the period of ocean acidification and massive dissolution of seafloor carbonates.
To collect sediments from the distant past, the scientists need a precision tool, or even better, a high-tech time machine. And this is exactly what the George's Resolution is equipped to provide.
If you take the JR, the boat itself, and you add to it all the scientists and the technicians that are on board, you can think of the JR as a true time machine. As you drill down into the ocean bottom, you're drilling back in time. And you bring these cores up onto deck, and you have no idea what time period they came from, but it's the people on board the JR that tell us that story. If you come into the core lab, and we're opening one of these cores where we think is around one of these really interesting time period where the world is changing, sometimes you open it up and you miss it, but other times you open it up and you see the world change before your very eyes, and that's super exciting.
As different cores are analysed, the new information gets combined with existing data to further unravel Earth's secrets. This is all part of this very exciting scientific process. As you see, these scientists don't work alone in isolated laboratories. They operate as a team. They discuss, debate, and they adapt their plans to get the most out of their investigations. It is a very dynamic, creative, and exciting process with a lot of human interaction.
It's not like you're operating, in a cubicle in the office someplace, doing tax returns or something. This is everybody working together. How the world works in order to accomplish anybody's goals.
Like many scientific endeavours, this expedition was full of surprises, twists and changes in the plot. In some cases, old ideas had to be abandoned and replaced by new ones as their understanding of Earth's climate history advanced.
So we went out to sea with a set of data that suggested what we were going to recover when we drilled a hole in the bottom of the ocean. But drilling a hole in the bottom of the ocean is always a surprise because things are always different than you actually think they are. And in this case, we had to revise essentially our drilling targets because we discovered that the subsurface geology wasn't actually what we thought it was at the beginning of the cruise. But we changed the strategy and it turned out it was very much more successful as a result.
There's little white spots, look at that.
But then the spots are below what we think of the boundary too, so this is pretty cool. So if you right here have this transition from dark clay to light clay. It doesn't look like much, but ask Antarctica what's going on, and it'll be no ice and ice.
And then, after 2 months at sea, the expedition is over. But the science continues, just in different settings and often with new collaborators. The scientists go out to the institutions to continue their research in even greater detail. They need to share their findings with other scientists around the world who will be critical and perhaps question their ideas. So sometimes it's 2 steps forward, 1 step back. Remember what Dick Norris told us earlier about being wrong.
My experience is that I'm almost always wrong. That the original idea I came up with is actually not a very good explanation for the way nature really works. And in many respects, I think that that's the very best possible outcome. Because if it turned out I'd been right to begin with, I must not have asked a very interesting question. But because I'm wrong, and I'm discovering how I'm wrong, and then also what the alternative explanations are, and eventually coming up with what I believe is the correct answer, it is just terrifically more exciting to be part of that kind of process.
At important times along the way, the data and conclusions drawn from the data are written up by the lead scientists and submitted to be scrutinized by other experts in the scientific community. Only when it passes their review is the work published. From there it can be used in a variety of ways. In science, one investigation is almost always part of a much larger story. The Newfoundland Expedition is only the most recent of its kind and was focused on uncovering the climate history in the North Atlantic. Previous IODP expeditions, such as Wilkes Land, have investigated climate change in other parts of the ocean and published their findings for others to use and build on. Publications from the Newfoundland Expedition will further expand what we know. And the more we learn, the more questions arise. This is the never-ending cycle of science. It's both exciting and challenging. And it's the way science really works.
I hope you guys like that. They could show you way more than what I could talk about and show you pictures of what we do at sea. But that ship, that's the ship I've been on every time. And we do go out for 2 months at a time usually. And I've been out there as a sedimentologist. What's coming up next? I said there was one site in the Arctic that I'll be part of the expedition team on coming up next year. And before I do that, have you guys ever done Pole Everywhere?
Yeah.
Do you have your cell phones with you? Can you come out for a second? I forgot I was going to do it. So text St. John KE to that number, 37607, and then answer this question. If you feel like it. This is something I do in my big class. And they will show up as you guys text things. 2, 37607.
Thank you.
Now, if you were middle and high school kids right now, you'd already have like full sentences up on that.
Yeah, I'm like, I don't think I brought this.
That's fine. It's a different time.
Good luck with that, right?
It's gonna show up on the slide.
Yeah, it'll show up on the screen once you guys submit things. There you go. So somebody in the room said that. All right, number one, response. Anyway, so if you, yeah, science isn't straightforward, it's way more fun. It is way fun. The moving arrow shows that science is it's cyclical. And then it's not linear. I can tell you, most of my students that come in, they still think, It's like, oh, no, it's so much more interesting. More questions than answers. It's thinking in and outside the box. Right.
Well, Dr. St. John, you also agree.
You can call me Kristen.
Well, it's my opinion that it doesn't start with the question, but it starts before that.
I guess I usually think, yes.
There's some observation of something.
And that is
And the
typically what
questions come.
I completely agree with it. That I think it really starts, there's something you observe. In most cases, sometimes there's something you've thought of and you've got a question. But I think often there's something we've seen, observed in some way.
That triggers
The question. I completely agree. Well, anyway, this process, I like what we're putting up here. That's great. This poll everywhere, we're paying for it, in our department, but you can do it on a trial basis for up to 25 people texting you at a time. So if you had like some special thing with students that you wanted to do this with, you're allowed to have the text.
Well, it encourages them to share because it's anonymous.
And that's been really good for the big class that I teach. Nobody wants to raise their hand, and so I can before CAPS happens, but I mix it up and use this. And I've got, Sandra's so great. I know we're a little, I'm a little off topic, but, so when I was in grad school, and I'm just like so intense, so working, I was like, blah, everything is like my work, my research. I remember I'm not a coffee drinker, I'm a tea drinker, and I got there's some brand of hot tea that has quotes on the little tab. Is it Celestial Seasonings? I can't remember, but this was like a while ago, so this is like in the late 90s. Anyway, I got one once, and it had a quote, was it, oh my goodness, was it Wordsworth, or it was a little poem. To see a world in a grain of sand and heaven in a wildflower, to hold infinity in the palm of your hands and eternity in an hour. It's like, oh my gosh, and that became, that's the frontispiece for my dissertation. So, I was like, that's exactly what I'm doing. It's so wonderful. So I was like, it was meant to be. And anyway, so I'm gonna go on. I have another question, but I think maybe for time's sake, we aren't gonna do this text one right now. But I just wanted you even to be aware that this can be like a fun technology. What I'll do though instead is I'm going to go on and to kind of wrap up. I said there's one more, what's happening next. And next summer from mid-August to mid-October, so for 2 months, I'll be the co-chief scientist for this expedition, IODP Expedition 377. So this means I'm not the sedimentologist now. I'm the lead scientist, co-lead scientist with Rudy Stein, who's in Germany. And he and I were both involved with the previous Arctic coring expedition in one capacity or another. And there were really big surprises on that past expedition. In the video they talked about sometimes you go to a place and you're not getting what you thought. Well, we got it was just surprise after surprise. It was like the home run of scientific ocean drilling, except there was a gap in the seismic data that we used to try to target, like, I think we should go here, I think we're going to have the nice layers, this is going to give us what we want. there was a surprise, and we got everything that was there, but there was a hiatus, there was a gap in the record of about 30 million years. Yeah, yeah. In fact, it's that time period that in the video it was saying PETM, really hot, everywhere's really hot, and then it went, and Antarctica starts growing ice. We had the PETM really hot, we saw it in the Arctic. The Arctic was like Florida during the PETM. And we missed the transition that when Antarctica goes, and I'm saying Antarctica, and I mean that, when Antarctica, we know Antarctica goes into a glacial state, and we want to know what's going on in the Arctic during that time. So we're basically going back. We're trying to go and get a complete stratigraphic record. We're going to move our location some. These are very complex drilling operations and support operations. We'll have 3 ships. This is taken from a helicopter and circled. There are 3 ships from the Coring Expedition back in 2004. That's the drill ship. These are the 2 ice support vessels. They're icebreakers. This is a Russian nuclear icebreaker, and this is, I think it's Swedish, I can't remember. But they have to break up the big slabs of sea ice so that this ship can stay in one place for weeks at a time without getting crushed, you know, because there's nobody up there to help you. So I was just in Germany a couple weeks ago. The first week of classes, I had to go to this meeting in Germany to plan this upcoming expedition and start being informed by the different technical groups about do we have the right ice ships lined up or not? We might have, yes, thank you, going back and forth by helicopter from one ship to another every day. We work 12 hours a day, 7 days a week at sea. So, yeah. So here's our plan. So we're going to leave Tromsø, Norway next summer in mid-August. We'll go up. This is where the drilling was before. There's the North Pole. Okay, we're going to go up on that same submarine ridge, but we're going to go closer to Siberia. So in between the North Pole and Siberia. And we'll be on site for a couple months. And then what we'll do is come back down and around, and we're actually going to go to Bremerhaven because that's the closest port to Bremen, where the repository is. Where some people are like, oh, look at those big warehouse things. So back to that, right? So to wrap up, then I have some ice rafted sand from the Central Arctic in the room with a microscope over there. Some microfossils from the Gulf of Mexico and an ocean core from the Gulf of Mexico. I also have we didn't have enough of these, but I have some. They're USBs from the geology department. If you think that your counselor or you or there's a student that might be interested in geoscience, give it to them. It tells them, whoever takes it, about the program. And I also have some mini posters that my students in my upper level class, they presented their research, the class-based research on the cores here from the Gulf of Mexico at the Southeastern Regional GSA meeting. So I have some examples of what students did in a college class for research, if that's something that you might want to show your students in high school or middle school. And I'm happy to be a resource for you as well. The back of your handout now. What I circled at the top, joydesresolution.org. If you go there, they have resources for media, for scientists, but then I circled for educators. So you can go to that, and when you open that, you see other things. When you scroll down, you see different things. You can get replica cores, not real cores, but replica cores. You can get all sorts of teaching resources. There are some other things that are kind of fun that you can, pencils and things they'll send you for free that are little core pictures. They're like pictures of, you can get the PETM on a pencil. And then the other thing more for you guys is applying to be a education officer at sea. And so that's something. And then if you click on this whole School of Rock thing, this is something that, in my first slide, it was about how, as you introduced me, how I do geoscience education research, and I also am a paleoceanographer, paleoclimatologist. The education side has been very much bridged, where I helped start this program, School of Rock. And I'm only involved in it a little bit now, but this is where we put teachers on the Joydes Resolution or other ships when they're in transit for free. And it's like you're getting a semester course, in 1 week as they're just trying to move the ship from one place to another. So sometimes these opportunities come up, and you have to apply. But that's something that I'd be happy to connect you more to the people who do it if you'd like. So, but I better stop because I can see we're out of time.